Howdy. The purpose of this video is to start to introduce structural properties of materials. First, we're going to talk about stress and strain. So if I'm designing any sort of structure, be it a skyscraper or be it a simple linking element in some sort of machine or mechanical design, ultimately, I need to know what kind of stresses is that element going to undergo and how much will it strain, how much will it deform. So because we're material scientists, we're focused on the underlying material properties. So we'd like to get away from any geometric effects that are going on. Because of this, we work with stress and strain rather than with forces, loads, and absolute deformations. And so I'm going to explain a little bit about why and where stress and strain come from. So first, let's think about a design. Let's say we have some element and it has a length and it has a cross-sectional area. And if I put a load on it, a force, it's now in tension, and it would naturally deform a little bit. And so this elongation I'm going to call delta L. So that's the change in the length of the material in response to this force. So let's think about this same exact material, except now I have twice the cross-sectional area. So naturally, you would say that it would not deform as much. And in fact, it'll deform about half as much. And the reason for that is that if I envision dividing this material in half, then each cross-sectional area is that original A. And now each area only would have to carry half of the overall load. And in response to carrying half the load, if we're elastically deforming, it's only going to elongate half the same extent. So this is an example where we would like to normalize to remove this geometric effect. And so what we do is, instead of talking about forces on materials, we talk about force per unit area. And we call that stress. Stress equals F over A. If I came back to this same exact example and I had twice the force over twice the area, my stress now equals 2F over 2A, and I would have the same stress. And so in that case, my elongation would be the same amount. Stress has units of either newtons per meter squared, so force is in newtons. Area, usually given by meters squared, and this is also defined as a Pascal. Or in English units, you could use pounds per square inch, or sometimes written PSI, pounds per square inch. We're going to stick with the SI units in this case. Okay, so that's stress. Let's think about strain a little bit, though. So I'm going to start off with the same exact case. Cross-sectional area A, length L, my deformation is delta L. So what if, instead of starting with this initial element, what if I start with something twice as long? And again, you could, intuitively, you would probably say that it's going to elongate more. And the reason for that is, again, I can separate it into two different halves. I can say there's L on the top half and L on the bottom half. And both of these elements L are undergoing an equivalent force. And so they're both elongating an amount delta L. And so when I add that together, I end up with a total elongation of 2 delta L. And so again, I'd like to normalize for this geometric factor. I'd like to work in a set of dimensions where I can talk about the intrinsic material properties rather than the geometry of the material. And so rather than talking about elongation, usually what we talk about is strain. And strain is defined as the elongation over the original length. And so this is unitless. So delta L could be in meters, but the original length would also be in meters, and so those would cancel out. So strain is unitless, although sometimes you will see units of length per length, so meter per meter, for example. Okay, so usually what we look at are engineering stress and strain diagrams. So stress is typically shown on the vertical axis and strain is typically shown on the horizontal axis. And these are a little bit in reverse of how we usually think of things in terms of independent and dependent variables. Because oftentimes you're saying I will apply some sort of a strain to a material, what is the resulting strain that I get? I'm not sure I said that right. If I apply some sort of stress to a material, what is the resulting strain that I get? But you can also think about the other way around. If I allow if there's a certain allowable strain, what is the maximum stress the material can undergo? And so if I were to want to read one of these diagrams, all I would do is I would say, okay, there's some point here. So let's say I'm undergoing a stress of a 350 megapascals. What is the resultant strain? So that is point A on the curve. I drop down and my strain, this is 0.05, that's 0.10, so the strain is about 0.07. Usually an example problem would be a little bit more complicated than that. So maybe I would give you an area and a length. And I could say, okay, let's apply some sort of force to the material. So let's say I'm applying 350 newtons. Well, the stress equals force over area. So 350 newtons. Let's say the area is 1 millimeter squared. So that's 0.001 meter squared. So that is going to equal 350 megapascals, if I did my math right. Hopefully I did. So I now know what the stress is, and I can calculate a strain from that. So I say my strain is 0.07, but oftentimes I'm looking for what the resulting elongation is. So remember, strain is defined as delta L over L. So if I know the strain is 0.07, in this case my initial length is 1 meter, and I want to know what the elongation is, I can simply bring that over here, and 0.07 meters equals the elongation. Okay, so in summary, we've defined what stress is. Stress is force per unit area. And we've defined what strain is. Strain is elongation per original unit length. And we use stress and strain because we want to get at intrinsic material properties. We want to get away from forces and elongations, which are dependent on the volume of material that you're looking at. Finally, we just did a little exercise on how to read a stress-strain diagram and calculate values off it.